number of ways that you can think about black holes, but one nice way in to the subject is to think about something that's much more familiar. Thinking about escape velocity. Let me describe what I mean through a couple of sequences here. So imagine that you are on the surface of the Earth. So let's sort of zoom down right to our planet. And we ask ourselves, if we fire a projectile from the surface of the Earth upward, what will happen? And we all pretty much know what will happen, right? So if we take a cannon and we fire a cannonball at a fairly modest speed, it's going to go up, it's going to come back down. If we fire it with a somewhat larger speed, it'll go up higher, but still it'll come back down. But finally, if we launch it with the right speed, it will go up, and it will just barely escape the gravitational pull of the Earth, and it will go off into space. And that speed required for that to happen is what we call escape velocity at the surface of the Earth. Now, what is the escape velocity at the surface of the Earth? Yeah, someone actually said it. What is it, 11.2? Kilometers per second. Thank you. Wow. A gold star in the back there. About 11 kilometers per second is what you need at the surface of the Earth. But here's the question. If you were to look at a different planet, one that's bigger than the Earth, what will happen? Well, again, you can pretty much picture what will happen. If it's bigger, it's more massive, you're going to need a bigger cannon to fire that cannonball with higher speed because the escape velocity will go up. It'll be larger than it is at the surface of the Earth. But of course, if you have that big cannon, you actually fire it, the cannonball will go up. And again, if its speed is bigger than the escape velocity, it will be able to get away. But now I want you to think about something a little bit less familiar. Imagine that this cannon is not firing cannonballs, but it's firing balls of light, photons. Now, light goes really quickly, right? I mean, light speed, what is the speed of light? Everybody uses different units, which is nice. 671 million miles per hour, 300 million kilometers per second, right? Meters per second, I should say. So at that high speed, of course, light will easily be able to escape and be able to go off into space. But here's the interesting thought experiment. And this is a thought experiment that goes way back. This is an experiment that this fellow over here, John Mitchell, this is in the 1700s, right? Long time ago. He asked the following question. He said, look, what if you were to imagine looking at, say, a star like the sun? Now, clearly, the escape velocity at the surface of the sun is much less than the speed of light. So certainly, all the light that the sun emits easily gets away. But just as the escape velocity of a planet goes up if you make it bigger, more massive, he asked, well, the same should happen for a star. So let's imagine making the star bigger, where the escape velocity goes up. Now, if it's still less than the speed of light, the light will get away. But he asked, what would happen if you made the star so big that the escape velocity at its surface would be bigger than the speed of light? Right? In that case, he imagined that if you made that gigantically massive star, light could not get away. The escape velocity would be bigger than the speed of light, and if light doesn't get away, the star would go dark. A dark star. Now this is, again, in the 1700s, right? So he is thinking purely in a Newtonian framework. That's the only description of gravity that we had back then. So the natural question is this musing of John Mitchell, right, this theologian, this natural philosopher from the 18th century, does this idea have relevance when you start to think about gravity in the manner that was given to us by this fellow over here, Albert Einstein? Because I think, as we all know, in the early years of the 20th century, Einstein rethought our understanding of gravity, and he gave us the general theory of relativity, in which gravity is now thought of in a completely new way, not the Newtonian description. Gravity is thought of as warps and curves in the fabric of space and time. So Einstein takes this idea, this new way of thinking about gravity. He writes his famous paper on the general theory of relativity. This is in 1915. This paper becomes widely circulated, and indeed about a year later, 1916, on the Russian front, there's a German astronomer, mathematician named Karl Schwarzschild, and he's out there in the trenches charged with calculating artillery trajectories, and somehow, just by coincidence, what happens is Einstein's paper just kind of goes by. He grabs a hold of it, and he gets so captivated by Einstein's ideas that he forgets about artillery trajectories and starts to calculate with general relativity. And he finds that if you have a spherical body that you crush down to a very small size, according to Einstein's math, the warp in the fabric of space will be so extreme that nothing can pull away. Not even light can pull away. So it's now a modern-day version, if you will, of what John Mitchell had imagined, an object that goes black because light cannot pull away from it. So roughly speaking, it would be as if you had a flashlight near the edge of one of these objects, and when you turn on the light, instead of the light going off into space, the light gets pulled down into the hole, into the black hole. This is the modern-day version of what a black hole would be. Now, the term black hole, it turned out this was coined on 112th Street and Broadway. I'm not joking. At the Goddard Institute of Space Studies on 112th and Broadway, John Wheeler was given a talk, and this way of describing these dark stars came up, and Wheeler pushed this idea. He popularized this, he advanced our understanding of it, but this is where the term black hole comes from. Now, this, of course, is a sort of cartoon version that gets at the basic idea. For those that want to see it a little bit more precisely, here's really what goes on. Near the vicinity of a black hole, and if you don't understand this, it doesn't matter. We can put down a space-time diagram, if you remember from high school. This is where we have time on this vertical axis, and you set off a beam of light that fills out a cone, so-called light cone. And what happens is the geometry of space and time is so distorted by a black hole that beyond what's called the event horizon, the direction of time and space is so twisted that as light propagates, it cannot get out of the edge. It cannot go beyond the event horizon of the black hole, and that's why no light can get out. That's why the black hole is black. Now, natural question is, okay, these are interesting ideas, but how in the world would one of these objects come to be? And people began to think about this idea for a long time, 30s, 40s, 50s. And let me give you one possible scenario by which the kind of object we're looking at, a black hole, would form. And for that, we can imagine that we have a large star, like a red giant. To support its incredible weight, this star has nuclear processes taking place in the core that generate heat and light and pressure that props the star up. But sooner or later, the star uses up all of its nuclear fuel, and at that point, it can't support its own weight, so it begins to implode. And as it implodes, it gets hotter and denser, finally setting off an explosion that ripples through the star. And when the explosion reaches the surface of the star, it causes the outer layers to explode. And what remains, if the star was big enough to begin with, is a tiny core, a dense core that can no longer support its own weight at all, and it will collapse all the way down into one of these objects, these black holes. That's the idea of how these objects could form. And what we'd like to do here tonight is explore our current thinking about these objects. Are they real? How would we actually see them? And can we get any insight into what happens inside of these spectacular objects? And to do that, we are going to bring out some experts who spent their careers examining these very questions, and let's get to them right now. So our first guest is one of the world's leading experts in observational astrophysics who heads UCLA's Galactic Center Group, best known for her groundbreaking insights on the center of our galaxy. She's the winner of, among other things, the Crawford Prize in Astronomy from the Royal Swedish Academy of Science and a MacArthur Fellow. Please welcome Andrea Ghez. All right, also joining us is an astronomer at the Harvard-Smithsonian Center for Astrophysics who leads an international collaborative project called the Event Horizon Telescope, whose goal is to image the edge, the event horizon of a black hole. So please welcome Shep, Doeleman. All right, so thank you both for joining us here tonight. Let me just begin with sort of one general question. So people have been thinking about this idea of black holes for a long time, as I said, all the way back in the 1700s, and a lot of research has been done, thousands of pages of calculations. Do you think that there are really black holes out there, or are theorists' imaginations overworked?
I think it's pretty clear that there are black holes out there. Of course, I'm a little biased.
Since you spent your life trying to observe them, yes, that's it.
And it's important to think about the fact that there are two kinds of black holes.
Yes.
The black holes that you were just talking about, the ones that come from the lifespan of stars, and then the supermassive black holes that we think are at the center of the galaxy.
And those are the ones that you've actually been studying in some detail.
Yes.
So we're going to get to those in just a moment. But Shep, your general view is more or less the same, or do you think there's a chance that it's a red herring, that these black things are not really out there?
Oh no, it's beyond a shadow of a doubt. I really think they exist. I mean, there's all these lines of evidence. You know, we see these terrifying engines at the centers of galaxies that spew out these jets on either side of them, and the only thing that can power them are supermassive black holes. So everything is pointing to the fact that these really do exist.
Good. So I'm glad you're saying that, because had you both said no, I don't know what we would do with the rest part of our discussion here today.
Right.
But that's great. So Andrea, your work, as I understand it, has been focused on the center of the Milky Way galaxy. So first of all, just give us some sense of what you think is residing in the center of our galaxy, and then we'll try to look at the evidence that led you to come to that conclusion.
So we're pretty convinced that there's a supermassive black hole at the center of our galaxy. And
how big is supermassive?
Yeah, well, when we say supermassive, we mean a million to, well, in the case of our own galaxy, 4 million times the mass of the sun. And in terms of these really big ones that are at the center of galaxies, that's on the low end, because we think about things that are 1 million to 1 billion times the mass of the sun.
And for a million solar mass black hole, like how, like for the sun, let's maybe start simple. If the sun was turned into a black hole, what would its radius be?
It would be about the size of a college campus.
Now, it depends which college we're talking about.
Let's talk about NYU.
Good. So a couple kilometers across.
Right, yeah.
For the one in the center of the galaxy, how big do we think it is?
It's about 10 times the size of the sun, so about 10 million kilometers.
Wow. So it's a big object, but it still follows the same basic pattern that it has an edge, an event horizon, and all the standard lore would apply to it. It's just on a bigger scale.
Right. It just scales simply with math.
With mass.
So the
Good.
math is simple.
Yeah. So what evidence do you have that it is a black hole? Can you sort of take us through that?
Yeah, so to prove that there's a black hole directly, what you want to do is you want to show that there's a lot of mass inside a small volume or inside a small region. In particular, you'd like to show that it's confined within its Schwarzschild radius that you were just talking about.
So Schwarzschild radius is the radius for a given mass, where if you can crush the mass within that radius, it will naturally turn into a black hole.
Right, and so that's what the size that we're talking about, because of course the black hole itself is infinitesimally small. So this isn't the abstract size, and so our job...
Could you just clarify that? So when you say that you're talking about when the black hole forms, the matter crushes down to a small size.
Yeah, so the idea of the Schwarzschild radius is that no light can escape it, as we were just talking about. But it's also true that once you get the mass to that scale, gravity will overcome all other known forces, and there's nothing that can stop the collapse of the object. So from a scientific point of view, once you've shown that a mass is within its Schwarzschild radius, you have come up with the proof of a black hole. So from the point of view of somebody who's hunting for black holes, your job is to show that there's some amount of mass inside a small volume. So the way we've approached it at the center of the galaxy is to look for the stars that are at the heart of the galaxy and to develop techniques that allow us to not only see the stars that are that close, but that allow us to observe how they go around the center. So if you want to find the center of the galaxy, you can look up in the night sky and find the constellation of Sagittarius. It's the teapot, and the teapot pours into the center of the galaxy.
Is that right?
That's your roadmap.
So convenient.
So convenient. And if you look up at the night sky, not in, of course, New York, but in a place that you can actually see the night sky, you can see the Milky Way. And the Milky Way is that band of white light that comes from the stars, but there's also a lack of light, which is from all the dust. So you can't actually see the center of the galaxy at wavelengths that your eye detects. So a key to the work that we've done is to use infrared technology. So looking at light that is just longward of what your eye detects, maybe where a TV remote control works.
Yep.
And that allows us to see the stars that are at the center of the galaxy.
And what have you found?
And we've found that they go, well, one, that we can see them, which is rather amazing, and that they go around the center of the galaxy quite fast. So my favorite star in the galaxy, its name is SO2, goes around every...
What's its name again?
SO2.
Okay.
It probably needs a better name.
Yeah, it's real catchy. Yeah.
So if you have a better name...
We'll leave it to the audience to figure that out.
But you can use actually Newton's laws of physics to show that if you go around every 16 years and you measure the size of the orbit, which is about the size of our solar system, that shows that there's about 4 million times the mass of the sun inside this incredibly small region. And to give you a sense of the change of our knowledge or our understanding of what resides at the center of the galaxy, we've increased the density of dark matter by a factor of 10 million compared to what was known before our work. So in a sense, we've advanced the case for the existence of supermassive black holes by that amount. I mean, think about anything in your life that you'd like more of and being able to get 10 million times more of.
Right.
And that's what's happened at the center of the galaxy.
Right, so the basic argument, as I understand it, is you're tracking these stars, and their motion can only be explained if there is a black hole of that mass residing in the center of the galaxy.
You're basically weighing what's at the center.
So is this actual data
This
here?
is data. This is the real thing. So we've looked at 2 versions of it. One is the flat version, which was playing just a moment ago, and it showed my favorite star. And this is actually a bigger view of the data that we've taken over the last, and I can't believe I'm saying this, 25 years.
Have you been involved with it since the beginning?
This is my baby.
It is.
Oh yeah. So in fact, it's interesting to reflect back because when I first proposed this experiment, when I first got my job at UCLA, I thought I had a good idea. It was actually turned down. They said the technique wouldn't work, and even if it did, we wouldn't see stars, and even if we saw stars, we wouldn't see them move. So it was a lot of no, no, no's.
Right.
And in fact, we were asking to do a project that was only 3 years long, just to see that stars were moving fast. No one anticipated that they would move so fast.
How fast is fast, just to give a sense?
Like 3 million miles an hour. So they're hauling, and it's kind of it's rather remarkable that we can measure something on a human time scale. And so as this project has gone on, and maybe we can talk a little later about how, what it takes, the technology has changed so much that it's enabled us to do more and more sophisticated kinds of work. So this 3-dimensional animation actually shows the kinds of stars that we see at the center of the galaxy, and almost every single prediction for what we should see near the black hole is inconsistent with the observations.
What does that mean?
That means it's job security.
So you're trying to figure it out.
Yeah.
But it's not inconsistent. yet with, say, the general relativistic predictions.
No, so there's both the physics side of this work, where you're trying to ask physics questions like, do supermassive black holes exist? How does gravity work near a supermassive black hole? So where we are today is that we can or at least in my opinion, we can definitively say that the supermassive black hole exists, and then where we are, actually, we are so in the middle of this. Can we test Einstein's theory of general relativity?
And that is what you're doing now, if I understand. Like, we're in actually a special time at this very moment, right?
Yes, we're in such a special moment. I can't believe I'm actually sitting here as opposed to being in Hawaii, where we take all our data.
Well, thank you for taking the time away. But tell us what's going on.
So the reason I'm so excited, and we've been preparing for this for years. So we've been doing this.
Wait, there's no chance you're going to miss like this special moment by being here?
Well, fortunately, I have grad students who are on the case. So we've been using the Keck telescopes, which are pictured here, for 25 years, and watching the star that goes around every 16 years. And if you want to test Einstein's theory of general relativity near a supermassive black hole with these stars, what you have to do is first make your first go around. That gives you a baseline of what part of space these stars are probing.
And that's 16 years right there.
That's 16 years right there.
Okay.
I can date my various moments in my life around the star. And then what you want to do is you want to catch it the next time it goes through closest approach. And that next time was the year 2018. So I've been thinking 2018 or bust for a number of years. So we're in it. We're in the season. And for us, there really is a season because the Earth goes around the sun. So, and because we're looking at infrared light, you're going to hear from Shep, there are different kinds of light, so Shep doesn't care about the sun. I care about the sun.
I care about the sun. I care about the sun. I'm a sun worshiper.
Because the Earth goes around the sun, there's only a part of the year that we can see the center of the galaxy at infrared wavelengths. So for me, we can see it from roughly March to roughly October. So there was the beginning of the season, and through these roughly 6 months, this star is experiencing incredible accelerations and is experiencing the most extreme forms of gravity as it makes its closest approach. So actually, there are 3 key moments. One that happened April 10th. One that happened roughly last week, and one that's happening in September that are going to nail down this experiment. So it's an exciting moment for us, and to see the signal emerge from the data, it's just a treat to be a scientist.
So if I understand correctly, so you actually have a prediction based on the general theory of relativity of what the trajectory should be.
Well, here we have to be a little bit careful because there's a series of kinds of experiments that there's a series of tests of gravity. One is how the light from the star makes it from the star to us. In other words, how it escapes the curvature of space-time.
Yep.
That's actually the first thing that we're getting at this summer. The next thing is then how the object itself moves through space-time, which is actually should emerge over the next few years. So again, and if you keep going, and of course that's what we want to do, you can actually measure the spin of the black hole. So this experiment just keeps getting better.
Right, and it's particularly interesting, I gather, because most people think that Einstein's general relativity has been confirmed, but is that the right way of thinking about it?
Well, it's one of the gravity is one of the 4 fundamental forces, but oddly enough, it's the least tested of those forces. So it's been tested in some regimes, but it's never been tested near a supermassive black hole. And in some sense, a supermassive black hole, black holes in general, represent the breakdown of this theory. So what you want to do is you want to get as close as possible to that point where you actually know that theory is no longer holding up. And I think we have to have today all sorts of pieces of evidence that says this theory is fraying at the edges. So we just push that frontier forward by a large amount in a direction that hasn't been explored before. So
in principle, you could find the first concrete evidence that we need to go beyond Einstein's ideas to really describe what's going on. I mean, the best of all worlds, that would be the outcome of 16 plus years of observation.
Well, the best outcome is actually just figuring out what's really happening near the black hole, whatever it is.
Yeah. Spectacular. So, Shep, you're also in the business of looking at black holes.
There's no business like black hole business.
No business like black hole business. And so you're going about it a different way. So we're hearing about infrared light as the probe being used to, in Andrea's work. You're using what, radio signals?
Yeah, we're using radio waves. It turns out that black holes, in a paradox of their own gravity, are some of the brightest things in the sky, right? And that's because of a very simple construct. All the gas and dust is trying to get into a very small region. So it heats up to hundreds of billions of degrees around Sagittarius A star, the supermassive black hole in the center of our galaxy. And it radiates in infrared, that Andrea looks at, and also radio waves, even a little bit in X-rays. So if you want to look at a black hole, you can come at it from many, many different angles.
Now, critical to both of what you're saying is you're not really looking at the black hole. You're looking at its effect on its environment, right?
Yeah,
so you can't actually see it, per se.
Exactly. What happens in the black hole stays in the black hole.
Yeah.
Let's just get that out of the way right now. But what we do is we tease around the edges, right? So in that cannonball analogy you had before, light was leaving the black hole, but it also orbits around the black hole. Just think about that for a minute. Light orbits something, right? And it goes around in a circle. And Einstein, 100 years ago, when he came up with this general theory of relativity, those equations show that you should see this silhouette of light around the black hole, and that's because of these light orbits around. So we look at it and we see light moving around the black hole, and it gets brighter on one side, on the other side. You see something that should be about 5 times the Schwarzschild radii across, right? So you know how big it should be.
So the event horizon is here, and you're looking at 5 times that distance from the center.
Exactly. So you never see inside the black hole, but you see outside, and that shows us the geometry of space-time. When you see something like this, when you see this shadow feature, you're really looking at the deepest puncture in space-time that we can imagine.
Right.
And the question
now, is this what you guys, I mean, can you share with us what you guys have seen? This is the Event Horizon Telescope, I gather, that you're talking about.
Right. So the question is, if you wanted to zoom in by orders of many, many thousands and see what was happening right at the edge of a black hole, you'd have to go way beyond where Andrea sees her stars and go much closer. And those stars are about 1,000 times farther out than this silhouette that you're seeing here.
Right.
And if we could measure the size of this silhouette and the shape, we'd test Einstein's theory of gravity right at the edge of the black hole. Right?
But how are you doing that? Is it a handful of radio telescopes, I gather?
Yeah, so to see something this small, these are the smallest objects in the known universe, right? Black holes are tiny. And to see them, you need magnifying power. And as it is with all telescopes, the bigger the telescope, the more magnifying power you have. Now, we can't make one huge telescope that sees radio waves. What we do is we install atomic clocks at multiple radio dishes around the world. We record data, and then we play it back at a central facility, and we create a virtual telescope as big as the Earth ourselves. These are some of the people who work at these various places.
How many teams are there?
Well, we have 8 geographic locations right now, and we're going to 9 and then 10 the year after next. And when you stitch together all of these telescopes, you wind up getting a virtual dish that's the size of the Earth. That is exactly tuned, it turns out, to image the supermassive black hole in the center of our galaxy. And we've just taken some of the first data from this Event Horizon telescope 1 year ago, and we're crunching on the data now.
And what have you found?
I can't tell you.
Oh, come on!
No, so it turns out that if you really want to make one of these images, it takes a long time to calibrate the data. It's all about the details. A lot of people think that we just turn this telescope on and we'll see something immediately. But it's, we're nerds at heart, right?
Yeah.
And we just love to get to the telescopes and find all of these details. And it turns out that you really have to run down every single one of these possible sources of contamination in the data before you can be sure that you've seen this kind of shadow silhouette.
Yeah, we were able to actually talk to a couple members of the team who slipped us actually some of the data. I hope you don't mind if we show it here.
Oh,
can we just show this is actually, I'm understanding this is the most precise image ever of a black hole. Do we have that? Can we bring the lights down and show this? Is that doable? Yeah. So yeah. All right, there it is. Very good. Yeah. So thank you. That's good enough for us. Thank you. You looked real nervous there for a second, man.
I was like,
Yeah.
boom, boom, boom.
Yeah. So when will you be releasing? I saw an article just a couple of days ago, which is kind of a teaser, it seemed like, for a release of data that's coming up. Is that soon?
It'll probably be in the first part of 2019.
2019.
Yeah, because right now we're crunching the data. We know that the Event Horizon Telescope worked. So what we did was we also looked at quasars, supermassive black holes that are really far away, that are basically point sources. And everything seems to have worked perfectly technically on the telescope. So we know that all the systems are a go. And then we turned, all the telescopes swiveled to look at Sagittarius A star, the supermassive black hole in the center of our galaxy. Yeah. And we think everything is working fine there, but we're still crunching on the data.
So, and the data, I saw some article that had come from the South Pole, and you had to wait for the winter to clear to fly. Was that the kind of thing that's going on, or?
Well, so the whole point, as Andrea said, if you want to test Einstein's theory, you've got to go to the most extreme points in the universe. You've got to go to the ultimate proving ground, which is the edge of a black hole. And we have to go to some pretty extreme places ourselves, right? So we have teams that go down to the South Pole. We go to the tops of extinct volcanoes, where there are radio dishes that do the work that we want to do. We go to Hawaii, Mauna Kea, high desert plains in Chile. And you go up to these sites, and it's really a bit of a labor of love, because all of these teams go there, they work their hearts out, they capture data. And this technique that we use, this Event Horizon Telescope technique, is really the ultimate in delayed gratification, right? Because here's what you do. So when Andrea goes to her telescope, it's pretty straightforward. Conceptually, the light bounces off a paraboloid, it goes to the focus, that's it. Right? You get what you want right there. What happens with us is the light hits one of our dishes. It's stored through high-speed instrumentation that we've built over the last decade on hard disks, the same kind of hard disks that you would get in your computer. And they stay there until they're brought back on an airplane, because nothing beats the bandwidth of a 747 filled with disk drives.
Right.
Nothing, okay? Even when I'm walking down the hallway with two of these disks, I'm beating the fastest internet in the world, okay? And we bring them back together, and the operation in this supercomputer that we use is equivalent to light bouncing off of a perfectly shaped parabola joining in coherence. Right? So we play it back together, and we adjust it back and forth until we get it just right, and that effectively turns the Earth into a parabola, if you think about that. So all of this data has to come back, and if it's at the South Pole, it's in a deep freeze. Right? So we've got to wait 6 months just to get that data back. Right? So that's one of the delays that we've been facing.
Gotcha. Yeah. Now, you have done some simulations of what you anticipate emerging from the data, looking at the magnetic field in the vicinity of a black hole. Can you take us through some of the things that you anticipate emerging from the study? I think we have some things up on the screen.
Yes. So what you're seeing here is the best guess we have from high-speed simulations of what you would see if you had infinite resolution goggles, right? So you wind up seeing this shadow feature, this circular feature, with some jets leaving from the north and south poles. And that's because there are magnetic fields right around the boundary of the black hole. There's relativistic particles. They're orbiting these magnetic fields, and they're releasing something called synchrotron emission, which is kind of a characteristic radio emission you get from these kinds of sources. And it's so bright in that synchrotron emission that it shines out from the deepest part of the gravity well, right? So think about it. Everything has to go right. It's a Goldilocks situation. You have to be able to see through the Earth's atmosphere, and radio waves can do that. You've got to be able to see through the distance between the Earth and the galactic center. Radio waves can see through that.
How far is that, just to give people a sense?
Well, it's about 25,000 light years away.
Good.
Right? So it's, this black hole is not threatening to us right now, right? We observe it. It's nice. So these radio waves can go all the way to from the black hole, but then we're not done yet, because it has to go through the hot gas swirling around the black hole, right? And then it has to go all the way down into the gravity well. So it's a Goldilocks situation because we meet all those criterion with radio waves. And it turns out that the Earth happens to be just the right size, so that when you look at radio waves with a wavelength of 1 millimeter, they're perfectly tuned to take the picture of Sagittarius A star.
So with an Earth-sized dish, it's just the right amount of resolution.
Yeah, so sometimes nature throws us all these curveballs, well, we can't do this, or this is hard. This is one case where everything's falling into place. And so we really think we have a good shot at taking the first image of a black hole.
And do you have a chance as well of finding a deviation from the general theory of relativity? Can this be viewed as another extreme testing ground?
Well, look, it's never a good idea to bet against Einstein. Okay, I don't make it a point in my career to do it, but it is a trust but verify situation. Okay, I mean, he was a very smart guy. Let's just put it that way. But every theory needs to be tested.
Well, when you say he's a very smart guy, that's true, but he wasn't a great fan of this idea of black holes at all, right? I mean, he kind of didn't think they were real.
Well,
so he was a little bit off on that one, right?
Okay, so he had one bad moment. Okay, one bad moment. But this really speaks to this kind of golden age that Andrea was talking about. With the Event Horizon Telescope, with the observations that are being made by the Keck, we're really in this discovery space for black holes. And we could be at the moment when we can start to answer these questions, like, do black holes exist? Was Einstein right at the very black hole boundary? I mean, you showed Schwarzschild in the trenches in World War I.
Yeah.
And he died later that year, actually. So this was his last big discovery. And he wrote down the Schwarzschild metric, and he gave what
the shape of space outside a black hole.
The shape of space outside the black hole. And now we're kind of engaging in this handshake across 100 years, where we're kind of completing this circuit. And we're saying, you made these intense predictions, and we're just at the point now where we might be able to test them.
Right.
And that is extraordinary. And it speaks to the fact that science is not linear. We don't go from point A to point B. We don't say, we're going to march and test this. It's very erratic. And that's why Einstein felt black holes might not exist. It took 100 years for them to become part of our lexicon,
right.
Part of the reality of our everyday conversation.
Now, do either of you or both of you, as you're working on your observational projects, do you have pet ideas or pet theories about what the next phase beyond Einstein might be, or do you just basically just go forward into the data, the observations, and that's the only thing that's really driving you? Or do you have an idea of what might be the next phase of this understanding of gravity?
Well, let me just take this for one second. I'm a realist. I'm kind of a craftsman at heart. Like, I like to go to the tops of mountains and make observations. I like to see what's around the black hole, right? I can understand and wrap my brain around the light that's coming outside the event horizon. What's inside the event horizon? That's a question that is hard to even ask, let alone answer.
Well, you just asked it.
I did ask it.
It's harder to answer it, I think.
I did. It's easy to wonder at, But for example, one thing we're looking at with the Event Horizon Telescope is to see if that silhouette is not round. What if it's distorted? Okay? And if it's distorted, then we have some framework of understanding how general relativity itself might be violated to give us those strange shapes. So we're betting on Einstein, we're betting it's going to be circular, but if it's not, we have some ways of understanding what might make it non-circular.
Yep. So we're winding down to the end of our section, but Andrea, I wanted to ask you a question, which is, how do you proceed in an era when you might be going beyond Einstein? When do you know that you're right? When do you know that things have coalesced to the point that you're willing to make a statement of that sort?
I think that's such an interesting and important question that we're really in the thick of, because if you see things that don't make sense, you don't have a context. You're kind of you're out there and you're exposed, and you have to convince yourself that what you're seeing is physics as opposed to experimental error.
Right.
Error. So I think there's an interesting philosophical point here about how do you convince yourself you've got the right answer.
Yeah, I mean, there was an interesting case with Bicep 2.
Oh, yes.
A few years ago where some have said that they so knew what they were looking for that they were biased in assessing what the data was telling them.
It's a classic thing called confirmation bias. So, and this kind of work where we have such a respect for Einstein and his ideas that we go in with a premise that it must be correct. So it is interesting in terms of how you actually design your team's work to avoid getting the result you believe to be true and allowing your team to really trust what the data is telling you. So I think that's certainly my goal as a scientist, to get to that point where you're really just listening or paying attention to the information that might be unexpected, but to try to remove your desire to have any particular answer, be it Einstein right or be it Einstein wrong,
Yep.
just to be open to whatever the answer truly is.
Right.
Yep.
Well, I should say, all of us revere Einstein, but at the same time, how thrilling would it be if either or both of you find evidence that we do need to go beyond the insights that he gave us 100 years ago. So we wish you well, and we'll have you back a year or two. Maybe then you'll be able to give us some insight into what you guys have found. So everybody, please join me in thanking Andrea, Ghez,
Thanks so much.
Shep, Doeleman. Thank you very much.